at the top of page 2, on the handout, I have copied an example that uses what is called a contingency table. I know you cannot see it because it's much smaller, so I'm going to copy this because I need to discuss what I'm trying to do with this. Contingency table. So the marital status and males and females. For contingency tables, make sure that you have another column that gives us totals. Okay? So quickly, you don't have to copy it if you have it. So I'm going to say never married, 41.6, 36.9, married, 64.4, 63.1, widowed, 3.1, 11.2, divorced, 11, 14.4, and separated, 2.4, 3.2. Not only that we need the totals for each column and for the total, grand total, but we also need the totals for each row. So let's do that, my calculator. 41.6 plus 36.9. 78.5. 64.4 plus 63.1. 127.5. 3.1 plus 11.2. 14.3. 11 plus the 25.4, and this is 5.6. Now I'm going to add these and create these totals and also the grand total. I will add them up and make sure I get this, and I will add them up and make sure I get this. Very important. So 41.6 plus 64.4 plus 3.1 plus 11 and plus 2.4. Correct my numbers. 122.5, 36.9 plus 63.1 plus 11.2 plus 14.4 plus 3.2, and I got 128.8. I'm going to add these two. 122.5, nope, 22.5, and I got 251.3. I don't trust my work. I will add up all these to make sure I get 251.3. So I'm here. 78.5, 127.5, plus 14.3, plus 25.4, plus 5.6. If I don't get 251.3, something is wrong. I have to go back. Good. So the contingency table has the columns, has the rows. I need a total for each column, and I need a total for each row, and I need the grand total. Now we are ready to answer the question. First question is, determine the probability that a randomly selected U.S. citizen, resident, whatever, 15 years and older, is a male. So again, we're going back to frequencies. So this is not the thinking method. I'm not thinking what can happen. I have the data. So when I have the data, I have to use the frequencies. So the probability that we select a male from the study, randomly select a U.S. resident, they're all 15 years and older, and the probability that we select a male. Obviously, it's the probability of selecting a male out of the total. So how many options we have for event M? And how many we have for the total, for the sample space? Outcomes, this is not probabilities. So how many are males in the whole study? $122.5. Great job. And what is the grand total?
Grand total is 251.3.
Yes, 251.3. Great job. Make sure that these numbers are all lower than 1, but greater than 0, of course. So 122.5 divided by 251.3, and I get 0.4874. Try 4 digits. 75. Next question. This was question A. Part B. Determine the probability that a randomly selected U.S. resident is widowed. Good. So how many outcomes we have for a widowed and how many outcomes we have for a total? Because it's out of the total. We know that the total is 251.3, but how many are widowed in the study? I'm sorry. So how many are total? How many are, we have the total, how many are widowed?
3.1.
That's why we created the totals. We're not talking about females or males. We are only talking about widowed.
14.3.
Yes. 14.3 it is. So I divide 14.3 and I divide by 251.3 and I get 0.0569. Stop if you have any questions, please. Moving on. Determine the probability that a randomly selected U.S. is widowed or divorced. So probability of widowed or divorced. What do we have to establish first before we proceed, before we try to find this probability? What are we trying to find first? We have to establish whether these two events are or are not what?
Disjointed.
Very good. Disjoint or not? Why? Because there are two possibilities. I can write the probability of W plus the probability of D minus the probability of W and D if they are not mutually exclusive. But if they are disjoint or mutually exclusive, I'm only going to do this. So this is not disjoint, and this is disjoint. I need to establish that, because I don't know how to calculate them. Back to the contingency table. So widowed or divorced? Widowed or divorced? They didn't make any distinction. Some people could be both, but there is no distinction here. In this particular study, this is what we have for widowed, and this is what we have for disjoint, for divorced. We do not have an intersection where we have people that are widowed and divorced. They exist, but we don't have it in the study. So are these two events disjoint or not disjoint? Disjoint or not disjoint? Can they happen at the same time? In real life, they can. Can they happen in our study at the same time? To be widowed? No. Since that cannot happen, we will say they are disjoint. So therefore, we will calculate the probability of W. We already have it. 14.3 over 251.3. We are going to add the probability of being a divorced person. What is the probability and how do I get it? How much? What do I have to write for divorced? Anyone? Anyone wants to help? Well, it's the same in the same way as we calculated the widowed. Divorced will be 25.4 out of the total. So plus 25.4 out of the same total of 251.3. We're going to add them up, and I get, what do I get? I get 339.7 divided by 251.3, and I will calculate. 39.7 divided by 251.3, and I got 0.1580. So that was part C. Maybe I should write them. So this was C, this was A, and this was B. And now we are moving on to part D. Determine the probability that a randomly selected U.S. resident 15 years and older is male or widowed. So part D. Male or widowed. What do we have to determine first? What do we need to determine first before we calculate? Because we don't know which formula to use.
If it's disjointed or not.
Very good. If it's disjoint or not. We'll figure it out in a minute. Back to the contingency table. Male is this, and widowed is this. Do they have a common element? Do they have a common outcome? See the difference between widowed and divorced? No common element. No outcome at the same time. But look here. Male, widowed. So are they disjoint or not? Anyone? Not disjoint. So I have to write P of M plus P of W minus P of M and W at the same time. Great job. Do we have P of M? Of course. 122.5 over 251.3. Do we have P of W? Yes, we do. 114.3 divided by 251.3. Do we have M and W? No, we don't. Can anyone give us the probability of M and W? And how do we calculate it?
They share the same one. It's 3.1. They both share 3.1.
Over
the total.
Exactly. They do share 3.1, and the probability for that will be out of the total. I used, of course, this because it's the same, the denominator is easy to calculate. 122.5 plus 14.3 minus 3.1. And final answer, 133.7 over 251.3. And I divide by 251.3, and I get 0.5320. Any questions? Any questions? Last time we talked about the complement of an event, and if you remember, we wrote, so complement of event, any event, let's say event E, is E complement. And it's always the case that the probability of E complement is 1 minus the probability of E, and vice versa. Probability of E is 1 minus the probability of E complement. And when I apply this to our first example with the Venn diagram to determine a couple of them, and then I have 2 more examples for you in a minute. So I'm back and I'm going to graph it again. You don't have to go back to the previous pages. I'm going to copy it here. So here it is. Our first example was this. Sample space, 3, 4, 5, 6, 7, 0, 1, 2, 8, 9, and this is E and this is F. We determined that the probability of E, there are 3 elements out of a total of 10. Well, what would be the probability of E complement? E complement will be everything that is not in E. This will be E complement. E complement. What you see in yellow is E complement. No problem. So this must be 1 minus the probability of E, which is 1 minus 3 over 10, which is 7 over 10. What if now I want to determine the probability of 3 or 4 or 5 or 6 or 7. What will that be? It's this. Everything else. Everything that is not in E and not in F. How do I determine that? I will say 1 minus the probability that is in E or F. This will be the complement of that. I know there are 5. So I would get 1 minus 5 over 10 equals 5 over 10, which is 1/2. So this is how the complement works. See, these 2 are complementary events. This event and these 2. They're separated in 2 different events. And the probability of the sample space is 1. And we do have 2 examples in the handout. So let's go to page 3. At the very top, it's example 3 and example 4 are both about the same thing, and then we can continue. So these... Say it again.
I have a quick question.
Please do. Yes, Emma?
The one we did before. It says 1 minus 3 over 10 equals 7 over 10. I'm a little confused.
How we got 1 minus 3 over 10?
No, how you got the 7 over 10.
Okay. Okay. 1 minus 3 over 10 cannot be determined before I find the least common denominator. And 1 has denominator 1. It was multiplied by 10, so I have to multiply it by 10. 10 was multiplied by 1, so I multiplied the top by 1. So 10 times 1 is 10, minus 3 times 1, which is 3, and we get 7 over 10.
Okay, that makes a lot more sense. Thank you.
Better? Very good. Thank you for your question. Other questions? Anyone? Okay, back to example 3 on page 3 at the top. According to the American Vet Medical Association, 31.6% of American households own a dog. So the probability for one dog in a household is 31.6, which is the same with 0.316. What is the probability that a randomly selected household does not own a dog? So basically, I'm going to call this E for simplicity. So the probability of E having a dog in a household is 0.316. And probability of not owning a dog, not having a dog. But you can say, but I can have 5, or I can have 2. What's happening with that? Well, assuming that it's a dog or not a dog, anything else can be not a dog. I don't have a dog, or if I have 5, it's in this category. Anything other than one single dog. So obviously this will be 1 minus the probability of having a dog. So the probability of E complement is 1 minus the probability of 0.316. And you calculate that, and what am I getting? I'm getting a 4, I'm getting an 8, and I think I'm getting a 6. So this is 68.4%. Next question, example 4. I want to add a couple of questions here, not just these two. So we have the data represents the travel time to work for residents in Connecticut. Okay, less than 5 minutes. The frequency is this, 24,000, between 5 and 9, between 10 and 14, and etc., etc., etc. Okay. Part A. What is the probability that a randomly selected resident has a travel time of 90 or more? Well, there is only one of 90 or more minutes. But the thing is that I have to calculate, I have to add up, I have to find the total. So let's find the total first.